Hey everybody, in this lesson we're going to talk about mechanical advantage, so let's not delay the inevitable. So how do simple machines work? If you remember from our last video, this was the last slide of it, which is why I did not spend a ton of time on it, because I knew I would spend a bunch on this one. So what is input force? Again, input force is the amount of force applied by the person to the machine. So it's the amount of force that you put in to whatever work you're trying to do. The output force is the force that the machine actually applies to the task. If the machine does its job well, the output force is going to be much, much greater than the input force. So when a machine takes a small input force to get a big output force, that's called mechanical advantage. Yes, I would know mechanical advantage very well. All mechanical advantage is a ratio. So we have the output force over the input force, okay? And that gets us a ratio. Now, there are two types of mechanical advantage. One is ideal, one is actual. The ideal mechanical advantage is purely theoretical, okay? It cannot be achieved in real life. This is because friction is not taken into account for ideal mechanical advantage, all right? We will get into actual mechanical advantage here in just a minute, but ideal mechanical advantage is important for us to figure out efficiency, which we will have to determine in 4-5. So, ideal mechanical advantage, IMA, equals the distance of the effort force divided by the distance of the resistance force. So we need effort on top and resistance as the denominator. Okay, so the distance traveled by the effort force divided by the distance traveled by resistance force. Let's take a look at 3 examples. Remember, there are 6 types of simple machines. We are going to be looking at 3 of those simple machines when it comes to mechanical advantage. So the first one we're going to look at is levers, or levers, whichever way you want to pronounce it. The ideal mechanical advantage is the distance from the effort. Remember, in this case, this would be a first-class lever where we have the fulcrum in the middle, we have the effort on one end, and we have the load on the other end, opposing ends of the fulcrum. This is the fulcrum. Okay, so the distance from the effort to the fulcrum, so in this example it's 15 meters, divided by the distance from the load to the fulcrum, that's 7 meters. So IMA in this case is 15 divided by 7, which is like, what, 2.1. Now, it's a ratio, right? We've said it's a ratio. Mechanical advantage is a ratio, just like Mach number is a ratio. And in both cases, neither is going to come with a unit. So we just have to worry about numbers when it comes to mechanical advantage. Our next example comes from the world of inclined planes. And again, it's the length of the effort over the length of the resistance. Effort in this case is the run or the length, the distance of the actual ramp itself. And then the resistance is the height of the ramp. So length of the ramp is 24 divided by height of the ramp, which is the resistance, and that will come out to a number somewhere around the range of 4 something, probably like 4.8. Give me a second. 24 divided by 5 is, man, I'm good. I should be like a mental math magician or something. Anyway, so that's 4.8, all right? So that means it is 4.8 times more efficient to move this block up this inclined plane than it is to pick up this block from here and lift it straight up. Now it has a trade-off. We have to go a really, really far distance to get that advantage, but it's still an advantage nonetheless. So it's it takes 4.8 times less energy to move this block up this ramp than it does to move this block straight up. Yay! Finally, the easiest one of them all, which is the mechanical advantage of pulleys. All we have to do is add up the number of ropes that are moving in the direction that the motion is occurring in the weight. So here is our weight. It is moving up, so we need to count all of the ropes that are moving up, with the weight. So this guy's moving up. That's good. That's 1. This rope is moving down, so that's against the motion, so therefore we don't count this one, n equals 1. Okay? In this example, we have a rope, and we have our weight is still trying to move up. So we have a rope, that's good, and we have this rope that is going up as well, so we count that equals n equals 2. All right? with me so far? This guy is moving up. Get the picture? Weights are always kind of moving up in these things. We have all of these ropes that are moving up with it, and then we have this rope again moving down against with the way that the motion is going. So we don't count this one because it's going against the motion of the weight. The weight is moving this direction, so we count 1, 2, 3, 4, and we have a total of 4N. And the mechanical advantage of this rigmarole is 4. It is not 5 because, again, this guy is going against the motion of the weight. Hopefully that was clear. You'll have a homework problem on that, and you'll probably, definitely, guaranteed see this in the near future. Alrighty, so that is mechanical advantage, excuse me, of pulleys. Now, actual mechanical advantage, where we take friction into account. So for those of you who are looking for differences in the world, the difference between actual mechanical advantage and ideal mechanical advantage is that actual mechanical advantage takes into account friction. Now, friction can be like if we have a box this way and a box that way, and he's going 10N, he's going 25N, we have a force of friction right here. Now, another way to do it is this box is going up and this box is going down, and this is the moving on, and this is the force of gravity, which we also know from our review of Unit 3 that the force of gravity is the resisting force. So in this case, when it's a vertical problem, the force of gravity will be that source of friction. So the force due to resistance, so that's going to be like the weight of the object, because weight, remember, is the force of gravity, and force of gravity is a resisting force. And then we have the force applied, which is trying to lift this booger up. Okay, let's look at an example. So a block is pulled up an inclined plane with a force of 20N. So our moving force is not, there we go, is 20N. And our block weighs, also force of gravity equals 325N. And what is the actual mechanical advantage? Remember, AMA equals force of friction, otherwise known as force of gravity, otherwise known as weight, divided by the force applied, or the force of effort, or the force of motion. However you want to put it, it's the force put into the system. So in this case, that is 325 divided by 20 gives us a number that will come out to be something in the realm of 16.3. Actual mechanical advantage, 16.3. Again, 325 divided by 20 gets you 16.25, but you know how we love to round to the tenths because that makes our answers so accurate. 16.3 is our answer for this sample problem. And that, my friends, is the end of 4.4. One video left where we talk about efficiency and power. So, see ya. Bye.